Imagine you are building a high-speed trading platform or a real-time multiplayer game. You have your database sitting in AWS because you love their RDS features, but your front-end and identity management are in Azure because your enterprise is deeply integrated with Active Directory. Every time a user clicks a button, a message has to travel from Azure to AWS and back again. Now imagine that handshake takes 300 milliseconds because the data is traveling halfway across the country and back through the public internet. Your users feel the lag, your application feels sluggish, and then suddenly the connection drops because a random router in a basement in Kansas goes offline. This is the nightmare of the unarchitected multi-cloud. Today on CloudCast, we are moving beyond the public internet and diving into the high-stakes world of the multi-cloud handshake. We are talking about how to wire AWS and Azure together so they act like one single seamless data center.
That sounds like a massive undertaking. I always assumed that since both AWS and Azure are in the cloud, they just kind of talk to each other automatically. Is it really that disconnected behind the scenes?
It is a common misconception. Think of AWS and Azure like two different massive cities. They both have their own internal roads, their own police, and their own utilities, but there is no natural highway connecting them. If you want to get from AWS town to Azure city, you usually have to take the public backroads. Those backroads are the public internet. They are crowded, they have potholes, and you have no control over the speed limit. If you want a professional, enterprise-grade connection, you have to build your own private bridge.
Okay, so we are building a bridge. I've heard of things like AWS Direct Connect and Azure ExpressRoute. Are those the tools we use to build this bridge?
Exactly. But here is the catch. You cannot just plug an AWS Direct Connect cable into an Azure ExpressRoute port. AWS and Azure are competitors. They do not have a physical cable running between their data centers. To make this work, you need a neutral third party. We call these Meet Me rooms or cloud exchange providers. Companies like Equinix, Megaport, or Digital Realty. They act like a neutral train station where both AWS and Azure have tracks. You meet them in the middle, and that is where the handshake happens.
So I have to buy a physical space in a data center just to connect my two clouds? That feels very hardware heavy for a cloud architect.
It used to be, but now it is mostly virtualized. You use a software-defined network provider. You go into a portal, you click a few buttons to request an AWS Direct Connect virtual circuit and an Azure ExpressRoute circuit, and the provider stitches them together in their fabric. This brings your latency down from maybe 80 or 100 milliseconds over the internet to under 5 milliseconds in some regions. It's like moving from a dirt road to a fiber optic vacuum tube.
5 milliseconds is incredible. But once we have the physical pipe or the virtual pipe, how do we make sure the data actually knows where to go? I've heard you mention route symmetry before, and it sounds like something that could break very easily.
Route symmetry is the holy grail of multi-cloud networking, and it is where most people trip up. Think of it like this. You send a letter from your house to your friend's house. You expect the reply to come back the same way. In networking, if a packet leaves Azure and goes to AWS through our fancy new private bridge, but the reply from AWS tries to go back over the public internet, we have a problem. This is called asymmetric routing.
Why is that a problem? As long as the data gets there, does it matter which road it took?
It matters immensely because of firewalls. Firewalls are like very strict security guards who remember everyone who leaves the building. If the guard at the Azure gate sees a packet leave for AWS, he expects to see that same packet return through his gate. If a random packet suddenly shows up at the back door via the internet claiming to be the response, the guard says, "I did not see you leave this way," and drops the packet immediately. The connection dies, your application breaks. To the user, the site is just down.
So route symmetry is making sure the data goes out and comes back through the same door. How do we enforce that when we have two different cloud giants who both want to be the boss of the routing table?
We use the language of the internet, BGP, or Border Gateway Protocol. BGP is the GPS of the networking world. AWS and Azure use BGP to tell each other which IP addresses they own. The handshake happens when you set up a BGP session between your AWS gateway and your Azure gateway. You have to be a bit of a traffic engineer here. You use things like AS path prepending or MED strings to tell the clouds which path is the favorite.
Can you break that down? What is AS path prepending? It sounds like something out of a textbook.
Think of BGP like a person choosing a route based on how many towns they have to drive through. BGP always wants the shortest path, meaning the fewest towns. If I want to make sure traffic stays on my private bridge instead of the internet, I make the internet path look like it goes through 50 extra towns. I artificially lengthen the path. When AWS looks at its map, it sees the private bridge is only 1 hop away, while the internet is 50 hops away. It will choose the bridge every single time. That is how we ensure symmetry. We make the paths we want look short, and the paths we do not want look long.
That makes sense. But what happens if the bridge collapses? If we have made the internet path look so long and undesirable, will it still work as a backup?
Yes, and that is the beauty of it. BGP is dynamic. If the private bridge goes down, that short path disappears from the map. Suddenly, the only route left is that long 50-hop internet path. It is slower, and the firewalls might need to be configured to allow it, but the traffic will flow. It is like having a primary highway and a secondary backroad. You only use the backroad if the highway is closed for construction.
I'm starting to see the complexity. We are not just talking about latency, we're talking about reliability. But let's go back to latency for a second. You mentioned 5 milliseconds. Does geography play a huge role in where we pick these meeting points?
It is the only thing that matters. You cannot beat the speed of light. If your AWS resources are in US East North Virginia and your Azure resources are in West US California, your latency will never be 5 milliseconds. It will be around 60 milliseconds because the light literally has to travel across the continent. To get that ultra-low latency handshake, you need to pick regions that are geographically close. AWS US East 1 and Azure East US are both physically located in Northern Virginia. They are practically neighbors. When you connect them through a local exchange in Ashburn, Virginia, that is when you get the magic numbers.
So the cloud isn't just a fluffy thing in the sky. It's tied to physical buildings. If I'm a developer and I'm seeing high latency between my multi-cloud services, the first thing I should check is the physical region?
Absolutely. If you have your database in Ireland and your app server in Tokyo, no amount of expensive private wiring will make that fast. You have to architect for proximity. But even when you are in the same city, you have to watch out for something called the hairpin turn.
A hairpin turn? Like in a car race?
Exactly. Imagine you are in AWS and you want to talk to Azure. Instead of going straight across the bridge, your traffic goes from AWS down to your on-premise data center in a different state, hits your local firewall, and then goes back up to Azure. You have just turned a 10-mile trip into a 1,000-mile trip. This usually happens because someone configured the routing to pass everything through a central corporate firewall. It kills performance. The multi-cloud handshake needs to be direct. You want to bypass the corporate office entirely for cloud-to-cloud traffic.
That sounds like a security nightmare for some companies. How do you keep it secure if you are bypassing the central office firewall?
You use virtual network appliances. You put a digital version of that firewall inside the cloud itself. You place a Palo Alto or a Fortinet instance right at the edge of your AWS and Azure environments. Now, the traffic stays in the high-speed clouds, but it still passes through the security checkpoint. You get the speed of the bridge and the safety of the guard.
Okay, I think I am connecting the dots. We need a physical meeting point. We use BGP to tell the traffic which way to go. We ensure symmetry so the firewalls don't get grumpy. And we keep the regions close together to avoid the speed of light penalty. But what about the cost? Is this handshake expensive?
It is a classic trade-off. Running traffic over the public internet is technically free in terms of setup, though you pay for data egress, which is the cost of data leaving the cloud. AWS and Azure love to charge you for data leaving their front door. However, if you use a direct connect or ExpressRoute, they actually give you a massive discount on that egress data. So if you are moving terabytes of data between the clouds, the private bridge might actually pay for itself just in data savings.
So it is faster, more reliable, and potentially cheaper for high-volume users. It sounds like there's no reason not to do it if you are serious about multi-cloud.
The only reason not to do it is complexity. It requires a solid understanding of Layer 3 networking. You can't just be a coder. You have to understand subnets, IP overlaps, and routing protocols. One of the biggest killers of the multi-cloud handshake is IP address overlap. If AWS thinks it owns the 10.0.0.0/16 range, and Azure also thinks it owns the 10.0.0.0/16 range, they will never be able to talk. They will both think the traffic is meant for themselves and never send it across the bridge.
I've run into that in local development with Docker. I can't imagine how hard that is to fix in a massive enterprise environment.
It is a nightmare.
You have to use something called NAT, or Network Address Translation, which is like giving everyone a fake name so they don't get confused. But it adds more complexity and more latency. The best architects plan their IP space years in advance. They carve out a chunk for AWS, a chunk for Azure, and a chunk for on-premise, making sure no two numbers ever touch.
This really changes how I look at the cloud. It is not just about the services. It is about the space between the services. If the handshake is weak, the whole system is weak.
That is the ultimate realization. You can have the fastest server in the world, but if the handshake is slow, the user experience is slow. You have to treat the network between the clouds as a first-class citizen in your architecture. It is the nervous system of your entire application. If the nerves are pinched or slow, the brain and the hands can't work together.
I think I finally get it. The handshake isn't just a connection. It's a carefully choreographed dance of geography, protocol, and policy.
Beautifully put. You are thinking like an architect now. We have covered the physical layer with cloud exchanges, the logical layer with BGP, the speed layer with regional proximity, and the security layer with virtual firewalls. That is the four-legged stool of multi-cloud connectivity. If you build on that, your cross-cloud applications will fly.
I feel much more confident about why we can't just rely on the internet for this. It's all about control. Controlling the path, controlling the speed, and controlling the cost.
Control is the key word. In the cloud, you trade control for convenience, but in networking, if you give up too much control, you pay for it in downtime. The multi-cloud handshake is how you take that control back.
Thanks for breaking this down. I used to think BGP was just for ISPs, but it turns out it's the secret sauce for the modern cloud developer too.
It really is. To wrap things up, remember, pick your regions wisely, watch your IP ranges, and always make sure your traffic knows the way home. If you do that, your AWS and Azure environments will shake hands and never let go. This has been another deep dive on CloudCast. I am the Network Ninja, and it was great having you here to ask the tough questions.
Thanks for having me. I'm going to go check my latency now.
Do it. And if it's over 10 milliseconds, you know who to call. We will see you all in the next episode, where we might just dive into the world of service meshes. Until then, keep your route symmetric and your latency low. Sign off, everyone. Clean connections and happy routing.